sample size. That's my last talk. 20 minutes late.
Half an hour you must take.
Half an hour. I'll finish at the earliest. So this is a slide I borrowed from a colleague. There are 3 rats here. It shows you my origins. The investigator reported that 1/3 of the rats were improved on the experimental medication. That's the person who's watching TV. 1/3 remained the same. That's the guy who's lying in the bed. And 1/3 could not be reported because that rat got away. Okay? The reason I put this slide up is because that's how at least I calculated sample size when I was a postgraduate student. And at that time 30 used to be like a magic number. Everything ended at 30. I think it still is today. Yes, and the reason I think is because 30 is amenable to the t-test. It took me a while to figure that out. I have a question for you, which you will answer at the end of the presentation. How many statisticians, sir, does it take to change a light bulb? So we'll come back to this at the end of the presentation. What I will do quickly is to talk to you about why sample size is needed, the concepts of hypothesis testing very briefly because they are linked to sample size calculation, the role of statistical errors which I mentioned in the morning, principles, problem solving very briefly, and I'll end with use of software. Why sample size? Same reason why statistics. And one of the most important reasons why we need to have a sample size calculation is ethics, which I didn't mention in the morning. I talked about cost, I talked about time, and I talked about personnel. But one of the most important reasons why one works with samples rather than populations is because it's completely unethical to try a new drug, a new device. There are 3 B's here. Right? That's A, B, 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 and B, C. So are these different? Yes. So you don't need a randomized trial to say that they are different. Are these different? Yes. That's an ophthalmologist here. Yes. Different? Yes. Yes. I'd say no.
The first picture, I say they are not different in some ways.
You will say that.
They have same red color eyes. So they are not different. It depends on your question.
So you always say depends for everything.
He is independent.
In statistics, we have a concept which is called as a null hypothesis. Now we have our friend Ajmal Kasam and a lot of other people, Arzan Guru. The null hypothesis concepts actually come from, they have their origins in law. So you start by saying that there is no difference, and then you try and prove that there is a difference or there is no difference. So your null hypothesis, and I'm talking here about randomized controlled trials, when you're looking at A versus B, it could be a drug, it could be a device, it could be a vaccine, it could be a surgical procedure. You start by saying that there is no difference between A and B. You say that the person is innocent until proven guilty. And this is your H0, H0, no difference. And the rest of it becomes your alternate hypothesis, that there is a difference. Right? Please answer this question. We are interested in investigating whether a novel drug is effective as a weight reducing agent. 30 clinically obese men with a BMI between 30 and 35 are randomly allocated either to drug or placebo for a period of 2 months. The body mass index is measured at the end of this period. Select all the statements that you think will provide an appropriate null hypothesis for the study. Null hypothesis is no change, no difference. At the end of the 2-month period, the mean BMI is greater in the placebo versus the drug group. True or false?
False.
At the end of the 2-month period, the mean BMI in the placebo is less than the study group? At the end of the 2-month period, the mean BMI is equal. True. The mean change in BMI from baseline to 2 months is greater in the drug group as compared to the placebo. The mean change in BMI from baseline to 2 months is equal. Right? So that is your null hypothesis. Now, in 1996, Callison et al. Showed a 25% reduction in mortality due to propranolol in patients with myocardial infarction. 66 patients, 65 controls were studied. The paper was rejected by the British Medical Journal because there was no statistically significant difference between the two groups. 2 questions. Are the numbers 64 and 66 small? A. And B. What about the clinical significance of this finding?
Small.
Small?
Small.
No students here? Let's ignore the first one. What about the clinical significance of this finding? Every time you treat 100 patients, you're able to save 25 lives. It's a significant thing. So why was the paper rejected? It's not statistically significant. It was rejected. So there's something called as a file drawer syndrome. It goes into the drawer. Which brings us to the question. If 25% reduction is clinically significant, clinically relevant, what went wrong? Now, this is a concept which I'll explain to you. This is fundamental to sample size calculation. Let's say you have A and B that you're comparing. There are 4 possibilities. The first possibility is that you find a difference between A and B. Actually, there is a difference. So, very good. Second, you don't find a difference between A and B. There is no difference. Very good. Third, you find a difference between A and B when there is no difference. That's a problem. Fourth, you don't find a difference between A and B when actually there is a difference. So when you do a randomized controlled trial, there are 4 possibilities. The first is finding a difference when a difference exists. Very good. Not finding a difference when there is no difference. Very good. When you find a difference when none exists, that is called as the alpha error. It's also called as the false positive error. It's also called as the type 1 error. Finding a difference when a difference does not exist. The last possibility is not finding a difference when a difference actually exists, which is your false negative. It's your type 2 error. It's also called as the beta error. Now, if I were to ask you, which of these 2 errors is the more dangerous of the errors?
False negative. False positive will overtake and false negative will miss out.
Which of these 2 errors is the more dangerous?
This is type 2 error.
Depends. Actually, the answer is depends.
It depends upon how significant the
Yes.
disease we are studying. If it's a dangerous disease, then you don't want to miss out anything.
What is the problem with the false positive error?
Overtake.
Finding a difference when a difference does not exist means that the MR will come to you and show you a paper which says that A is better than B, so you change your prescription. So type 1 errors alter clinical practice. Change your prescription, right? So you might end up using a drug or a device or a vaccine which is less safe, which is less efficacious. So it is perceived as more dangerous of the two errors. What happens if I were to tell you that the type B error is also equally dangerous? False negative. When you play the devil's advocate, you're missing out on an important drug. And this is what happened in malaria. Again, I come back to malaria. For the longest time, artemisinin derivatives, the Chinese molecules which we use today so frequently for falciparum malaria, people were unable to show a difference with quinine. Right? So quinine continued to remain the drug of choice until one large randomized trial actually showed that there was a significant reduction in mortality with artemisinin derivatives. India was one of the centers, and therefore there was a switch in prescriptions to artemisinin derivatives, which are actually safer relatively than quinine. So a lot of people actually argue that you might end up missing out on something which is really good. But the other way of looking at it is at least you have standard of care. Right? And like he said very rightly, it also depends on the disease in question. So if you have something like falciparum malaria, which is so important, producing so much of mortality, you wouldn't want to lose out on a good molecule. So the answer is, it depends. Last concept is the power of the study. Right? What is the power of the study? Beta error is not finding a difference when a difference actually exists. So finding a difference is 1 minus beta. Beta is not finding. So to find, you have to subtract beta. Beta error is conventionally set at 10% or 20%, which means your studies are usually 80% powerful or 90% powerful to detect a difference should a difference actually exist. Okay? The last concept I'll talk to you before I wind up is something called as one-sided and two-sided statistical test. So whenever you read literature, you come across this term, one-tailed test was used, or two-tailed test was used, or one-sided test was used, or two-sided. What does a side in statistics mean? A side in statistics refers to direction of movement of data. Right? For example, when you have blood sugar as your variable, blood sugar can go up, it can go down. Intraocular pressure goes up, goes down. Right? So most biological variables that we deal with on a day-to-day basis are capable of what we call as bidirectional movement. Right? So general rule of thumb is when you are not sure about your biological variable, always use a two-sided test or a two-tailed test rather than a one-sided or a one-tailed test. There are very few examples of biological variables which are capable of unidirectional movement, one of which is height. Supposing I were to argue that height is also a bidirectional variable.
It's true. Because the height is maximum in the morning and...
One is diurnal variation. What else? Osteoporosis, age, right? So height also is a bidirectional variable. So general rule of thumb, biological variables tend to be bidirectional. If you want to toy with sample size calculation, just go to Google. You type into Google PS software. P stands for power, S stands for sample size. This download takes about 2 to 3 minutes. Put it on your programs, and this is how your PS software opens up. It's from the Vanderbilt University. It's entirely free, and very useful resource for postgraduate students. These are all the various types of sample size calculations that are possible. We've discussed in the morning about data types. When you want to calculate sample size for categorical data, you go here. This is dichotomous. Di is 2, binary is 2. Right? So dichotomous data. And when you want to calculate sample size for quantitative data, right, then this becomes your t-test here. That's where you use it for the sample size calculation. I'll just summarize and end by talking about elements of sample size calculation. The way we've done these workshops earlier is that you actually have calculators with you, and we run formal examples and you actually get a feel of how you do it. But I'll just summarize what I've said. When you calculate samples, and I'll answer your question also, when we calculate sample size for categorical data, which is expressed as proportions, you need to know the proportion of successes in the first group, the proportion of successes in the second group, and what Dr. Alok was alluding to, what is the clinically meaningful difference between the two. In other words, when you have a two-group comparison, what is it that will make you switch from A to B? What is the difference which will make you change your prescription from A to B? And remember, this clinically meaningful difference is something which is entirely in your hands, and you must never leave it to the statistician. Right? When you deal with quantitative data, sample size calculations involve mean of the first group, mean of the second group, and the standard deviation, which you see, which is your variability. And in all of this, you fit in your values of the alpha and the beta error to give you a common sample size result. Right? It will appear completely Greek and Latin to you because we haven't had formal training on this, but essentially these are all the elements which go into calculating sample size. And for sample size for prevalence studies, you also need something called as the precision value. Right? For sample size calculation on prevalence is a beautiful online calculator called Naing's calculator, N-A-I-N-G. It's online, it's an Excel calculator, free and remote. So use that if you want to do, let's say, prevalence of osteoporosis or osteopenia in this audience. Single group studies, sample size for prevalence, use this particular calculator. Just a couple of take-home messages. When the difference between the groups that you study is very large, the sample size tends to be small. The higher powered you study, 90% powered studies will always have higher sample sizes than 80% powered studies. Remember that most biological variables that we deal with move bidirectionally, including height. Generally, when you're dealing with biological variables, use two-sided rather than one-sided tests. And another rule of thumb is when you use one-sided tests, which sometimes people do, you will end up with a smaller sample size rather than a larger sample size. Last couple of slides. When we were second MBBS students, we used to have this exercise. We used to have this pole, and there used to be a rat. There used to be a buzzer and an electric shock. We used to test the effect of antipsychotics. So the buzzer followed by the electric shock. So the rat initially doesn't figure out anything, and after some time, the moment he hears the buzzer, he climbs the pole because he knows that the electric shock will follow the buzzer. So instead of the rat, you have a frog here. So what you do is you have a frog with 4 legs. You shock the frog and it jumps 4 feet. Then you cut one leg and he jumps 3 feet. Right? And then you cut another leg and another leg. And finally he's got no legs. And what do you conclude? That a frog with no legs cannot hear. So the interpretation of any statistical data is never to be left to the statistician. The reason is, a statistician is one who will not accept that Columbus discovered America because he said he was looking for India. What is the take-home message here? You might find something entirely different than you started off with, but do not ignore your results. Columbus made an error in his power calculation because he relied on an estimate of the size of the earth which was too small. So ensure that you have the correct standard deviation when you calculate sample size, but he made one nonetheless and it turned out to have very fruitful consequences. This is something, I mean, all of you know this already, but just reiterating this, that always learn to distinguish between statistical and clinical significance. Something which is clinically significant may not be statistically significant. And something which is statistically significant may not be clinically meaningful. And I think as pediatricians or ophthalmologists or surgeons or whatever you are, a lot of time I think medicine relies on intuition, on past experience. So statistics, no matter how many lectures you may have, is going to help you only up to a certain point. Right? So remember that ultimately when you take decisions, you do not take decisions on groups of individuals, you take decisions on a single individual, often with insufficient data, and you will rely on intuition and experience, and nothing can substitute that. So how many biostatisticians does it take to change a light bulb? One, because they are accustomed to menial work. You don't ever tell them that. Two, because one may drop out. So add dropouts to your sample size calculation. That's your take-home message here. Three, because the probability of a biostatistician boring somebody else to sleep is 2/3, which I hope does not happen. None. Having the biostatistician's name on the protocol for changing the light bulb is quite adequate. So you will ask the IJO editor for this question. Don't ask me. And defense on the design of the light bulb and the purpose for changing it. I also think a lot in statistics is great. The defense, right? I would not be here if it were not for all these people that I've learned from. I'll leave you to read the last slide.
You mean it? Nice.
When you calculate the sample size,
Yes.
have we excluded the sampling bias and sampling
You should have
errors?
excluded. You should have excluded
But
sample
when
bias
the
and
author
sample.
sends the papers, they will say this is the mean sample, this is the sample size calculated.
Yes.
When I wrote back and asked, okay, was the sampling bias excluded? How was it excluded? I never got an answer for that question. So when I send you a question saying, okay, can you calculate the sample size of this study? Would you ensure that the sampling bias has been removed from that before you calculate the number?
Ideally, one ensures that sampling bias is removed from sample size calculations. There are various ways of doing a sample size calculation. For example, if I were to ask you that you have a study where you want to do a study, but there is no information available to you, how would you calculate the sample size? You wouldn't. In that case, you would do a pilot study. That's one message I always forget to give. Not all studies require a sample size calculation. When you're doing a study on something for the first time, it's a pilot study, you do not need sample size calculation. Second is, you often derive your sample size based on literature. So you have literature data which is available on mean or standard deviation or proportions or the variability. That's the second area from which you take. And the third is, if you really have nothing to go by, you do your pilot study and you derive your sample size from that pilot study data. So whatever data that you get from your pilot study will then act as the baseline for your sample size calculation. But bias and error is something you must eliminate, otherwise the results that you get will be completely odd.
So we mentioned that when we say this is sample size calculated after eliminating the sampling
You
bias.
don't say that, you just give from where you've taken your values. For example, if you say the proportions were 15% and 25%, how have you chosen those proportions? Is it from your own studies? Is it from literature? That's something you need to mention.
Can I just
Yes, ma'am.
like you said that supposedly there's no literature available for a certain
Yes, yes.
and you're doing
It happens
a
often.
yeah,
Yeah.
and you're doing a pilot study. Based on the results of the pilot study, then how further do you calculate the sample size?
You will get a pilot study for whatever you're looking at. Let's say you're looking at IOP. You will get a mean, you will get a variation, which is your standard deviation. That will then act as the baseline for your sample size calculation. So you will use that mean, that standard deviation, alpha error, beta error, and then calculate the sample size. The reason why it's confusing is because we haven't formally done the calculation by hand, but that will serve as the baseline for your calculations. And most of the times you do it online. It comes in a couple of seconds, you have your answers.
And many times it happens that when you calculate the sample size, really it becomes impractical to do that. So that time, I don't know what studies should be followed, but usually what we see that, okay, you are calculating sample size coming 1,000. It's not feasible to conduct 1,000 studies on 1,000 subjects. And you see the literature, most of the publication may be having only 70, 80, 90, 100. So can we follow that literature in case if you are getting like that? Or there is something which is on convenience sampling. So that...
See, most often what happens is when you have the difference, you have a delta which is very small. Looking at a very small difference between two groups, and your sample size becomes very, very large. In that case, you have one of two options. One is you do a multi-centric study. That means you divide an entire sample over multiple centers all over the country, in which case you have problems of funding, sponsors, etc. That's something that can be done. The other option for you to do a study with what you say is a convenience sample, but then what you will end up with is an underpowered study. So you might not set out to find what you set out. And it also again depends, I think, like one of the persons said here, it depends on the disease of importance. If you feel it's something really important and you do need to do a study, but you're not able to do it with a very, very large sample size, you will find a difference which is underpowered, may not be significant, but may be clinically relevant, in which case I would rather do the study underpowered than not do the study.
Sometimes might help in terms
Yes.
like this. If there are,
Sometimes author takes the shortcut and put the difference which is actually not possible. So if you have read the LOGIS study, low tension glaucoma study, that author has said the difference between the progression rate between the brimonidine and timolol in 5 years 25%. And if you know glaucoma, you know that in 5 years 25% progression is not possible. But having decided 25% difference, you get sample size which is small.
very small. So this is what is, delta if you...
Delta is very, very important. Yes. So what happens is most statisticians will actually manipulate the delta to give you the kind of sample size that you want, which is amenable, which will lead to an underpowered study. But I would rather do the study than not to do the study and find the difference. And if you still think that difference is clinically significant or meaningful, even with an underpowered, not significant study, it's still worthwhile.
Yeah.
Otherwise, you will have a file draw again.
But also sometimes...
if you do a large sample, even a small
Difference will get
statistically
magnified,
significant.
which may not be clinically meaningful. Absolutely.
And also this, if you suppose if there are 5-6 publications like this, which are all underpowered.
Yes.
So one
You
can
will
do
do a
meta-analysis
meta-analysis,
better.
yeah.
So that helps in that way. The disease is important, that's what you
The
said.
most important thing is to publish. Even if it is underpowered, do publish it, because somebody will pick it up in a meta-analysis, which will add to a well-powered study eventually. I think Sir's point is very well
The
taken.
problem of publishing about small sample, most of the good journals will not take it. They just refuse because it's small sample, statistically not significant, all this sort of reasoning will be given. And
No,
it
again,
will end up in a
depends on-
small journal, where people would not even.
Yeah, I think Basumati will vary. I mean, most journals are electronic online, but if somebody is doing a good literature search and doing a meta-analysis, I would rather publish it rather than not publish it, and then hopefully it will get picked up for the analysis.
It also depends on the importance of the subject, because even the good journals, with the subject is important, and even if it is underpowered or not significant, probably they will publish it.
No, they will include you as a part of the multi-center trial. If your study is good, they know that you are doing a good study.
No, how can they include it?
No, not the journal. What I am saying is they will suggest, okay, there are other researchers who are doing the same type of job. They say, why don't you all join as a multi-center trial and conduct this research?
Yeah, that is different. That is different.
I think a couple of questions.
If we are planning a pilot study, how do we need to fix a sample size for the pilot study?
No.
Then how do we define that? Yes,
It varies now. Again, the magic number 30, 10, 20, 30. It also depends on, for example, if it's a disease which is really rare, you only see maybe 10 patients a year or something, then you will take all those 10 patients. It's a disease which is fairly common. You can easily take 25, 30 patients. So there is no formula for piloting. Sample size for pilot studies, you take them as they come along. But your protocol and your research question and your objective need to be very, very clearly defined. Otherwise you will. And I think that's the lecture which is scheduled tomorrow. To me, that's the most important lecture in any research methodology workshop. Formulating your research question well and your objective well. Everything else is secondary.
Second, for rare disease, can you just guess based on our past experience?
Yes. You can do that. That's called as guesstimating. Guesstimating is permissible in sample size calculation, which is based on your own clinical experience of seeing particular patients with the disease. In clinical pharmacology, we call something called as a Lasagna's law. Lasagna's law states that the moment you think of a protocol and have a protocol, the patients dry up. So you start with a disease and then you don't see any patient.
No, it happens in clinical research also.
That's called Lasagna's law. Yeah. Yes, I think.
Yeah. What I want to say, if I need a 3,000 subjects for my study, and I have only 100 or 300, this should not discourage anyone to go ahead, do a study and publish it. Because you do with 300, but do calculate the proper sample size. In the conclusion part, you do write, among 300 subjects, I found this trend, but my study is not powered so, and I need a 3,000.
Yeah, I did see that earlier.
This trend is worth enough to carry on the further study, and I think no good actor will.
It's better to do a study which is underpowered than not do it at all. Publish it. Publish
it and calculate both and elaborate in the conclusion part. I think it should be accepted and published.
We've had a couple of studies in the past where we've shown deltas at 60% power and 70% power. So we've actually written in the discussion that if our study was 90% power, then this would have been the sample size. But because of constraints of time, patience, we've not been able to do it. And that will again be a baseline for somebody else and get picked up in a meta-analysis.
If I'm finding a very strong trend or I believe in that trend, I should go ahead and publish. I don't be discouraged because I don't have the 5,000 subjects, so my study is wrong. It is not. There is no question of wrong or right.
No, there is no wrong or right ultimately. There is no wrong or
right. Carrying on or something like that. This is the trend. Why if somebody else is able to do the very big study? So I should put my trend at least. This will encourage others, might encourage others.
Yes, I think you had a question.
What would be the scope of publishing a pilot study?
Very good. Very good. And I believe that the number of journals these days are increasing by leaps and bounds with print, electronics. So if your study is worthwhile, you feel strongly about your research question, do the pilot study and do publish it. Like you said, it will be your baseline for somebody else, rather than not doing a study. Pilot studies are very good as long as your hypothesis, your research question is well thought through. Then it is really, you must do it.
Pilot study also depends. Suppose something which is a very short study and you can get large number, but since you didn't have data, that's why you did pilot study. Then there is no point publishing pilot study. But something which is really important, you don't have enough cases, and even publishing 5 or 10 cases pilot is good enough. But also, the pilot study also always means that it's going to follow with the main study. So that you should not ignore. What?